Today in DC electrical circuits, we're looking at lab number 8, potentiometers and rheostats. The objective of this exercise is to examine the practical workings of adjustable resistances, namely the potentiometer and rheostat. Their usage in adjustable voltage and current control will be investigated. I've given you a reference section. It's Chapter 3 in Sham's Outlines, Basic Electricity, 2nd edition. It's Ohm's Law and Power, and they're talking about variable resistors. So before I show you the reference section, I just wanted to show you some examples of variable resistors or potentiometers. You can see here I have a fairly large one. It does have 3 leads going to it, so most potentiometers will have 3 leads going to it. This is a fairly large one, and it has an output shaft, and when you rotate it, it changes the wiper position. So this is a smaller potentiometer, and I just wanted to show you this one because it's all exposed. And you can see the center part here is the wiper arm. So as I move it around, it's actually going to change the amount of resistance between this leg and this point. So that is going to be a lot lower resistance than from this point all the way around to the other side. So this is another potentiometer, and what you do is you put a small screwdriver in there and you can rotate it from one side, and that's as far as it'll go, and rotate it all the way around to the other side. So this is a single turn potentiometer. And here's another potentiometer, and you notice it has 3 legs. You can always tell the wiper arm is the center leg. So you always have 2 outer legs and a center leg. And this one would be a multi-turn potentiometer. And I believe this one is somewhere around 25 complete rotations to move the wiper arm from one end all the way down to the other end. So this would be more of a precision type device where you wanted to control your resistance in smaller increments. Now looking at the top here, the 3006P is the package type. The 103 indicates that it's 10 times 10 to the power of 3, so this would be a 10k ohm potentiometer. So in Chapter 3 of your textbook, Ohm's Law and Power, we're interested in the section on variable resistors, and it says variable resistors are used to vary or change the amount of resistance in a circuit. Variable resistors are called potentiometers or rheostats depending on how they're used. So in figure 3-5, they've given you a graphic of what's going on inside a potentiometer. You can see there's a sliding arm and a resistive element. So depending on where this sliding arm is, will determine the amount of resistance between point A and B, which is very low here, or the resistance between B and C, which is very high. And the resistance between point A and C is always constant. So when the sliding arm of a variable resistor is moved, the resistance between the center terminal and end terminals changes. So I've given you an example here with the wiper arm around the other direction. So now between B and C is low resistance, and between A and B is high resistance, and between A and C is the total resistance. So in figure 3.6, they're showing us a rheostat to control the current going into a lamp. So basically the wiper arm is connected to one end of the potentiometer, and as the wiper arm moves back and forth, if the wiper arm's down this side, you can see we short out the resistor, so that would be very low ohms, so we get maximum current. So when it's used as a rheostat, it's used to control current. In figure 3.7, we can see it's used as a potentiometer, and that's to change voltage. So depending on where this wiper arm is, it selects between 0 volts and 6 volts. So at halfway, our output would be 3 volts. So in the theory overview, it says a potentiometer is a 3-terminal resistive device. The outer terminals represent a constant resistance, which is the nominal value of the device. A third terminal, called the wiper arm, is in essence a contact point that can be moved along the resistance. So today's equipment, we're going to be using the adjustable DC power supply, which is the Agilent E3630A. We're going to be using the digital multimeter, which is the Mastech MSM 9803. We're going to be using a 10K potentiometer, and it's going to be labeled 103 or 10K. We're going to be using a 100K potentiometer, which will be labeled 104 or 100K. We need a 1K ohm resistor, a 4.7K ohm resistor, and a 47K ohm resistor. I've given you the color codes for each of the resistors, and I've given you some examples of different potentiometers that I just showed you on the bench. I'm not quite sure which ones you're going to have in your kit. The multi-turn ones are going to be a pain to use. The single-turn ones are going to be quite easy. And you can see I've given you a note on potentiometers, so they're usually labeled things like 103 or 104. So we've got two schematics we're going to be using. Figure 8.2 is the potentiometer, and you can see that we're going to put a load resistor on it and load it down and see what the effect is on the potentiometer. We're also going to have a second circuit in figure 8.3. This is the potentiometer wired as a rheostat, and here you can see we're just going to leave one leg open and move the wiper back and forth, and it's going to have a load on it. So we're going to see the effect different loads have on this rheostat. Now I just wanted to jump to the tables for a moment here. What we've got is a potentiometer, and we have to rotate it fully counterclockwise, and then we're going to give it a quarter turn, half turn, 3/4 turn, and then turn fully clockwise. Now the thing is, if we have a single turn potentiometer, it's kind of easy to figure out where a quarter turn is. Now when I do my example of rotating a potentiometer, mine takes 25 turns to get from one end to the other. So halfway is going to be 12.5 turns, quarter way is 6.25 turns, and 3/4 of the way is going to be 18.75 turns. So I'll show you how to do that on a single turn potentiometer and a multi-turn potentiometer. So under procedure, step 1, the first thing we're going to do is use an ohm meter to check the values of your resistors and record the values under equipment, just to make sure that we have the right resistors to build our circuit with. So my 1K ohm resistor is 994 ohms. My 4.7K ohm resistor is 4.61K ohms. My 47K ohm resistor is 48.2K ohms. To measure the resistance of your potentiometers, put them into the breadboard and use 2 wires to connect the leads together rather than trying to get alligator clips on them. So the red lead will go to one end, you'll miss one pin, and the black lead will go to the other end. So when you look at the pins on the bottom of your potentiometer, you can see one lead at one end will go to the red bus, the other lead at the other end will go to the black bus, and then the one in the middle is not used. And you can see my 10K ohm potentiometer reads 9.82K ohms. You can see if you have a different style potentiometer, the lead spacing is a lot longer. So looking at the leads on this potentiometer, you can see one end of the potentiometer starts down here where the black wire comes in. The other lead is way down here. and the center leg is not going to be used. Just for reference, this potentiometer was 10.62 k ohms. This is my 100 k ohm potentiometer, and you can see it's labeled 104. So my 100 k ohm potentiometer reads 104.7 k ohms. So under equipment, I've recorded the model number for the power supply and the model number for the digital multimeter. I'm just going to X out the serial numbers because they're too difficult to get into and find. My 10 k ohm potentiometer measured 9.82 k. That was for the single turn potentiometer. I also have a multi-turn potentiometer just as an illustration. You're only going to have one of these two types of potentiometers, so use whichever one came in your kit. For the 100 k ohm potentiometer, I'm just going to use the single turn type, and then I've put down the values that I had for my individual resistors. So under step 2 of the procedure, they're saying in figure 8.1 there are several different types of potentiometers. I don't know what type you're going to get in your kit. It will either be a single turn, so you can move the wiper from point A to point B in a single turn, or it might be a multi-turn potentiometer, which means you may need 10, 15, 20 turns to get from one end to the other. So in this lab we're going to use a 10 k potentiometer and rotate the knob fully counterclockwise. We're going to measure the resistance from the terminal A to the wiper arm, W, and then we're going to measure from the wiper arm to terminal B. And we're going to record these values in table 8.1. Then we're going to add the two readings together, and it should come out to the nominal value of your potentiometer. So basically, if you have a 10 k potentiometer and it's turned halfway, the resistance from A to the wiper should be 5 k, and from the wiper to point B should be another 5 k, totaling 10 k. So looking at table 8.1, we have the position of the potentiometer. So that'll be the adjustment screw on the potentiometer. We can have it turned fully counterclockwise, a quarter, half, 3/4, or fully turned clockwise. So measuring your resistance between point A and the wiper arm, fully counterclockwise we should have 0 ohms, moving all the way up to fully clockwise at 10 k ohms. So this is the setup of my potentiometer. You can see I have the red lead from the ohm meter going to the first pin, which I decided to label as pin A. The second pin is the wiper, and the third pin is point B. Now I've marked on my potentiometer. This would be fully counterclockwise. This would be a quarter, half, 3/4, and fully clockwise. So putting a small screwdriver into the potentiometer, I can rotate it back and forth. So all the way back this way would be fully counterclockwise. And on my ohm meter, I'm getting 0.2 ohms. Now I've picked up my potentiometer and turned it around backwards. And you can see I'm now getting 9.82 k ohms. So I just wanted to show you, you can put your potentiometer in this way around, or you can turn it around 180 degrees and then put it in. It doesn't matter as long as you get the correct reading on your ohm meter. So it doesn't matter which way around you turn your potentiometer, as long as you remember that one side is going to be your A point, the center is your wiper, and the other one is your B point. So for me, my potentiometer in this orientation, calling this A and this the wiper arm, I'm reading 0.3 ohms. At a quarter turn, I'm getting 2.317 k ohms. So moving my red wire down a hole and my black wire down a hole, I'm now reading between the wiper and point B. and I'm now getting 7.52k ohms. So filling in my chart, you can see I had 0.2 between A and W and 9.83 between W and B. Added those together to come up with 10.03k. When I was at a quarter turn, I was at 2.137, and when I measured between points W and B, I was at 7.52k, and when you add the two numbers together, you come up with 9.657k ohms. So when we add these two columns together, we should always come close to our 10k ohms. So switching from the single turn to a multi-turn potentiometer, you can see the package is different. The spacing between the pins is different. Instead of the A pin and the wiper pin being beside each other, there's now one hole between them. And the B pin is a lot further back. The adjustment screw is on the side or end of the package. So I'm measuring between point A and the wiper. So in table 8.1, what I've done is I've determined how many turns it takes to get from one end of my potentiometer to the other. So this particular potentiometer is 25 turns. So halfway should be 12.5 turns, and a quarter way should be 6.25 turns. Now I know to adjust from one position to the next, I just have to add 6.25 turns. So adjusting this potentiometer 12.5 turns from fully counterclockwise, you can see my reading between A and the wiper is 5k ohms. I've now moved my ohm meter wire from point A to point B, and my resistance reading is 4.87k ohms. So in table 8.1, 5k plus 4.87k equals 9.87k ohms. I now have to rotate my screw 6 complete rotations clockwise. 1, 2, 3, 4, 5, 6. And you can see my reading between point A and the wiper is now 7.53k ohms. My reading between the wiper and point B is 2.387k ohms. Rotating my potentiometer fully clockwise, I'm reading 9.9k ohms. Measuring between the wiper and point B, I'm getting 0.3 ohms. So looking at table 8.1, you can see the resistance between point A and the wiper arm, and the resistance between the wiper arm and point B always adds up to the nominal value of your potentiometer. So under procedure, step 4, we're going to calculate the loading effects on the potentiometer using the circuit of figure 8.2. Now that's with 10 volts applied on a 10k ohm potentiometer. So we have to calculate the voltages from W to B at counterclockwise, quarter turn, half turn, 3/4 turn, and fully clockwise, and record these values in table 8.2. So this is the schematic figure 8.2 of the potentiometer, and you can see we have A point, B point, and the wiper arm in the center. We're going to be putting a load resistor on here, so we call it RL. And depending on where the wiper arm is, we're going to have the load resistor in parallel with part of the potentiometer in series with the other part of the potentiometer. So it becomes a series parallel calculation. So in order to help you with your calculations, I've got schematic equivalence for calculations, and you can see I have two resistors, and basically the wiper arm is going to be in the center. So we have the A part, some resistance, the wiper arm, some resistance, and then B. And we're going to be applying 10 volts to our circuit. So we want to know what the voltage is at point W. In the second column, we want to know V from W to B with a 47k ohm load resistor. So in the first case, it was simple voltage divider. In the second case, we have our load resistor in parallel with part of our potentiometer in series with the rest of the potentiometer. So I just wanted to show you the full page of calculations. You can see we have a set of calculations for fully counterclockwise, quarter turn, half turn, three-quarter turn, and fully clockwise. So I just wanted to show you a couple of examples here. So if we take an example where we have turned the potentiometer halfway. The first one is an example of finding out what the voltage at W with respect to B is with the output open, so no load resistor. So if the potentiometer is halfway, it's going to be made up of a 5k ohm resistor, the wiper arm, and another 5k ohm resistor. So to find the voltage at point W, it's simply voltage divider. 5k divided by 10k times the 10 volts applied equals 5 volts. Now when we put a load resistor across our potentiometer, so this is a 47k ohm load resistor, we now have 47k in parallel with 5k ohms in series with the 5k. So the first thing we need to do is find out what 5k in parallel with 47k is. In my case it was 4.5k. So now we have two resistors making up our potentiometer. The first one is 5k. The second parallel branch is going to be 4.5k. So to do voltage divider, we take 4.5k and divide it by the 5k plus the 4.5k times 10 volts, and it works out to 4.7 volts. In the next case, where we're using a 4.7k load resistor, we now have 4.7k in parallel with 5k, and that works out to 2.4k. So now using voltage divider, we have 2.4k, the parallel equivalent, divided by 5k plus 2.4k times 10 volts. And now the voltage at point W will be 3.2 volts. Finally, when we have a 1k ohm load resistor, we now have 1k in parallel with 5k. And that works out to 833 ohms. So now we have 833 divided by 5k plus 833 times 10 volts equals 1.4 volts. So as you increase the load on a potentiometer, increasing the load means increasing the amount of current. So when we have no load resistor, we have 5 volts. And when we have 1k ohms maximum load resistor, we're left with 1.4 volts. So in table 8.2, I've recorded all my calculations. So you can see that with a open load or no load on the potentiometer, fully counterclockwise, I should be at 10 volts. At a quarter turn, 7.5 volts. Half a turn, 5 volts. 3/4 of a turn, 2.5 volts. And fully clockwise, I should be at 0 volts. So moving on to procedure, step number 5, we're going to construct the circuit of figure 8.2. apply 10 volts to a 10 k ohm potentiometer. We're going to leave RL open. We're going to rotate the knob fully counterclockwise. We're going to measure the voltage from the wiper to the ground, record the value in table 8.2, and then continue recording voltages as the knob is rotated to the other 4 positions. So that's a quarter turn, half turn, 3/4 turn, and fully clockwise. So when we look at our schematic, we can see the positive of the supply is going to go to point A, the negative of the supply is going to go to point B, and the wiper arm in the center is where we're going to take our voltage reading. So depending on which potentiometer you have is going to determine which point is A, which point is B, and where the wiper arm is. W is typically in the center, and A and B are on the outer sides. So this is a single turn potentiometer, and as you can see, point A has the power coming in, point B has the ground going to it, and the wiper, which is in the center, goes to the voltmeter. So rotating the potentiometer fully counterclockwise, my voltage reading is 10.07 volts. Rotating a quarter turn clockwise, my voltage reading is 7.72 volts. Rotating to the halfway position, my voltage reading is 4.9 volts. Rotating to the 3/4 position, my voltage reading is 2.45 volts. Rotating fully clockwise, my voltage reading is 0 volts. So in table 8.2, for the voltage, a point W with respect to B, with an open or no load resistor, I've recorded my results. So under procedure, step 6, we're going to set RL to 47 k ohms, and we're going to repeat step 5. So on figure 8.2, which is our schematic, we can see between point W and point B, we're going to be putting our 47 k ohm resistor. So this is my 47 k ohm resistor, and you can see one lead goes to the ground lead. The other lead goes to the yellow wire that went to the wiper arm. So here's what it looks like with the potentiometer placed back in the circuit. With the center knob turned fully counterclockwise, you can see I'm getting 10.07 volts. At a quarter turn, I get 7.25 volts. At 1/2 turn, I get 4.64 volts. At 3/4 turn, I get 2.32 volts. Rotated fully clockwise, I get 0 volts. In table 8.2, for the voltage at point W with respect to B, with a 47 k ohm load resistor, these are my results. Under procedure, step 7, we're going to set RL to 4.7 k, and then repeat step 5. I've replaced my 47 k ohm resistor with this 4.7 k ohm resistor. Fully counterclockwise, I get 10.07 volts. At a quarter turn, I get 5.56 volts. At a half turn, I get 3.156 volts. At 3/4 turns, I get 1.74 volts. Fully clockwise, I get 0 volts. So on table 8.2, for the voltage at W with respect to B, with a 4.7 k ohm load resistor, these are my results. So under procedure, step 8, we're now going to set RL to 1 k, and we're going to repeat step 5. I've now replaced my 4.7 k ohm resistor with a 1 k ohm resistor. Rotating the potentiometer fully counterclockwise, I have 10.07 volts. At 1/4 turn, I have 2.872 volts. With the potentiometer rotated 1/2 turn, I have 1.446 volts. With the potentiometer turned 3/4 turn clockwise, I have 0.859 volts. With the potentiometer turned fully clockwise, I have 0 volts. So in table 8.2, for the voltage at point W with respect to B with a 1 k ohm load, these are my results. So comparing my measured results to my theoretical results, you can see they're off by quite a bit. But rotating the shaft is not an exact science, and I may have missed by a little bit. So under procedure, step 9, we're going to be using a linear grid. We're going to plot the voltages of table 8.2 versus their positions. Note that there will be 4 curves created, one for each load, but place them on a single graph. And then we're supposed to note how the variance of the load affects the line and control of the voltage. So in table 8.2, we're going to be using all our measured values. So V, WB open will be one line. V, WB 47K will be another line. 4.7K will be another line. And V, WB with a 1K load will be our final line on our graph. So on the horizontal of my graph, you can see I start with fully counterclockwise, quarter position, half position, 3/4 position, and fully clockwise. And for the vertical, we're going to have voltage, and it's going to be every 2 divisions is 1 volt. So that's 4, 4.5, 5 volts. So it should go all the way from 0 to 10 volts. So looking at my finished graph, you can see I have 4 lines. The first one is open. The second one is with the 47 k ohm load resistor. And you can see there's a slight variance between open and 47K. Then the third one is the 4.7K, and you can see it kind of sags over. And then the last one is the 1K. So as we increase the load on the potentiometer, you can see the load line is no longer linear. It's now more of an exponential type curve to it. Under procedure, step 10, we're supposed to calculate the loading effects on the rheostat using the circuit of figure 8.3. We have 10 volts and a 100 k ohm potentiometer. We're to record these values in table 8.3. Then we're going to construct the circuit of figure 8.3 and use a load resistor of 1K. We're going to rotate the knob fully counterclockwise and measure the current through the load. We're going to record this in table 8.3 and repeat this process for the remaining knob positions of table 8.3. So looking at figure 8.3, we can see we have a potentiometer, but we're only going to go from the A point to the wiper arm, and then we're going to put the load resistor in going back to ground. So this becomes a simple series circuit. So looking at figure 8.3, the rheostat, the applied voltage is going to be 10 volts, RL is 1K, and we have a 100 k ohm potentiometer. And we're just connecting between one end of the potentiometer and the wiper arm. We're going to leave the other end of the potentiometer open. And our rheostat's going to be either 0 ohms if the wiper's all the way down to point A, So the total resistance of the circuit is 0 plus 1K, so it's going to be 1K ohms. So using Ohm's law, I equals V over R, the answer is going to be 10 volts divided by whatever the resistance of our circuit is. So in this case, it's 1K. At a quarter turn, my potentiometer should be at 25K ohms plus the 1K in series. So I should have a total of 26K ohms. At half turn, it should be 50K plus the 1K. 3/4 turn, 75 plus 1K. And fully clockwise should be 100K plus the 1K load. So looking at table 8.3, my calculations are fairly simple. For fully counterclockwise, it's 10 volts divided by 1K, which is 10 milliamps. At a quarter turn, it's 10 volts divided by the 25K plus the 1K load. So that's 26K, and that's 384 microamps. At a half turn, it's 10 volts divided by the 50K plus the 1K load, and that equals 196 microamps. At 3/4 turns, it's 10 volts divided by the 76K, which is 131 microamps. And finally, fully clockwise, we have 10 volts divided by 101K, which is 99 microamps. So I have my potentiometer wired up here. This is a 104, so that will be 100K. The red line from the power supply comes in, goes to the first pin of the potentiometer. The wiper pin goes to the leg on the 1K ohm resistor, and the other leg of the 1K ohm resistor goes to the black lead going back to the common of the power supply. Now with the potentiometer rotated fully counterclockwise and my range set to 40 milliamps, you can see I'm getting 9.99 milliamps flowing through my circuit. Now rotating my potentiometer a quarter turn clockwise, you can see I'm getting 0.37 milliamps, but to get a more accurate reading I need to change the range on my ammeter. So by changing the range on my ammeter to the 4 milliamp range, you can see I'm getting 380 microamps. At a half turn on my potentiometer, you can see I'm getting 199 microamps. At a 3/4 turn clockwise on my potentiometer, I'm getting 122 microamps. And rotating my potentiometer fully clockwise, you can see I'm getting 94 microamps. So under procedure, step 11, we're going to replace the load resistor with a 4.7K ohm resistor, and then repeat step 10. So back on figure 8.3, we're going to be replacing the 1K ohm load resistor with 4.7K. So our first position, fully counterclockwise, we're going to have 0 ohms from the rheostat, or potentiometer, plus the 4.7K. So that works out to 4.7K. Then at a quarter turn, we have the 25K plus the 4.7, which equals 29.7K. At a half turn, we have the 50K plus the 4.7, which is 54.7K. 3/4 turn, we have the 75K plus the 4.7K, which is 79.7K. And finally, for fully clockwise, we have 100K plus the 4.7K, which works out to 104.7K. So in table 8.3, for IL, a 4.7K ohm load resistor, the formula becomes the 10 volts applied divided by the 4.7K equals 2.13 milliamps. At a quarter turn, it's 10 divided by 29.7K, which is 337 microamps. At a half turn, it's 10 volts divided by 54.7K, which is 183 microamps. 3/4 turn, it's 10 divided by 79.7K, which is 126 microamps. And finally, fully clockwise, it's 10 volts divided by 104.7 K, which is equal to 96 microamps. So back on my trainer, you can see I've replaced the 1K with the 4.7 K ohm resistor. And power goes to the first pin of the potentiometer. The resistor goes to the wiper arm or center pin of the potentiometer. The third pin of the potentiometer is left open. The other end of the resistor goes back to the common of the power supply. So with my potentiometer rotated fully counterclockwise, you can see I'm getting 2.13 milliamps. At a quarter turn clockwise, you can see I'm getting 383 microamps. At a half turn clockwise, you can see I'm getting 177 microamps. Rotating to 3/4 turn clockwise, you can see I'm getting 126 microamps. And finally, rotating the potentiometer fully clockwise, you can see I'm getting 91 microamps. So in table 8.3, under IL for a 4.7 K ohm load resistor, I've recorded my results. In some cases, they're going to be 100% accurate, and in some cases, they're going to be off by a bit, just depending on how far around you turned that potentiometer when you were adjusting it. It's difficult to get it exactly at a quarter, a half, and 3/4 every time you rotate it. We now have 6 questions to be answered based on your observations, the data in your tables, and the plot you generated. When you've completed your lab, leave it wired up so that you can show it to your instructor, and they will initial it to indicate that the lab is complete.